When looking at resistors organized in a parallel orientation within a circuit, it's solved similarly to the way we would deal with a series circuit. We have to take a few things differently into account, as the orientation, the geometry of the circuit is slightly different. We can start the same way we start with a series, in the sense that we know the overall voltage. We have 9 volts, so we have 9 volts to spend, so to say, when traveling through this circuit. So we know our overall voltage for this circuit is going to be 9 volts. We also know that we should name our resistors first as well. So if I call this one here R1, this one R2, this one R3, that'll help me fill out my data chart here based on the resistor 1, resistor 2, resistor 3. You can call them whatever you want in whatever order. It doesn't matter. You just need to be able to keep your information in this data table organized. So based on R1, we know that R1 is 3 ohms, R2 is 2 ohms, R3 is 4 ohms. Now, please don't get tripped up here and think that the total will always be the sum of these columns. Last example, in the series example, they will be, because in series you simply add them together. To find our total or equivalent resistance for this circuit, we have to take into account the fact that these are actually oriented in parallel. So hopefully remember that in order to determine the equivalent resistance, you have to actually add up the reciprocals of the resistances present in the circuit, no matter how many you have, so on and so forth. Hopefully you also remember that there's a shortcut. So if I want to find my equivalent resistance using a calculator, in this case for parallel, I'm going to add up 1 over R1, which is 3, 1 over R2, which is 2, and 1 over R3, which is 4. And if I actually take that answer and raise it to the -1, I will actually get my equivalent resistance for a parallel circuit. So if I put my calculator in here, we have 1/3 plus 1/2. Whoops, I have no idea what that is. 1/3 plus 1/2 plus 1/4. Now again, that's not my equivalent resistance. I have to raise that to the -1, and I get an equivalent resistance of 0.92. So my equivalent resistance is 0.92. That is my total resistance for this circuit. So 0.92. You don't necessarily need to fill in the units on this if you don't want to. It's good to make a note somewhere that your resistance is measured in ohms. So you know the equivalent resistance for this entire parallel circuit is going to be 0.92. Hopefully you're beginning to see if I have the resistance and I have the voltage, I should be able to relate those by Ohm's law, which again tells us that the voltage is equal to the current times the resistance. So if I would like to solve for current, I divide both sides by resistance and get my voltage divided by my resistance will give me my current. So in this case, what I'm going to need to look at here is my voltage, which is 9. I'm going to have to divide that by my resistance, which is 0.92. And what I wind up with is 9.78, we'll round that to. 9.78 amps of current. So if I have 9.78 amps, the one thing we could do with series is say, well, as we go through, the current would have to be all the same. Well, the problem with a parallel is, much like a river that then branches off, you have a different amount of current. If you think about it, the current leaving, or at the beginning of the river, will be the same as the current at the end in this case, because all these paths come back together. But once it hits these junctions, that current starts to split. So while you don't have the same amount of current per se in each of these, what you can say is that when I add the current in all 3 of these, when they all combine together back at the end, it's going to have to add up to 9.78 amps. So at this point, we can't say how much current is going through each of these. We don't know. The only thing we can say definitively is when I add the current in each of these, it has to add up to 9.78, because those 9.78 amps split between the paths that include R1, R2, and R3. An easier way to think of this is go back to our original example. You have 9 volts to spend. Every time you pass through a resistor, you spend some voltage. Well, you have to spend all of it by the time you reach the very end. You should also remember from previous videos and discussions in class, electrons, protons, depending whether you're talking about conventional charge, which is based on the movement of positive charges, or actual current, which is based on the movement of negative charges. If a charge wants to move through here, it's going to go through one of these resistors. Hopefully, if you're paying attention in class, you'll realize it's most likely going to want to go through here, as that has the least amount of resistance. So most electrons will try to go through here, least amount of resistance. And again, remember, the electrons would actually go this direction. I apologize, but I'm showing this based on convention. So the charge will want to go through the path with least resistance. The only charges that will go through here are those that kind of don't quite get in here. Not enough room, so they'll choose an alternate route. But most will want to go through the path of least resistance. So as I travel through the loops, I have three different options, hopefully you're seeing. If I'm a charge leaving this terminal, I can pass through here and return. My second option, if I was another charge, would be to bypass that and travel through here. And the third option would be to travel through the path that includes resistor 3. Again, you need to realize you're not going to have any charge that's going to kind of jump around and go through a bunch of these before coming over here to the other terminal. That would be like if you were, I don't know, leaving work and you wanted to get home, and rather than just driving home through the shortest route, you decided to drive home and then, I don't know, to another office building, and then back to your office where you work, and I don't know, back to school, and then pass a mall. You're not going to take this ridiculous route. You're just going to kind of go through, get back home as quick as possible. A charge or an electron is no different. So if we take a look at this, if I have a charge leave one terminal, well, if I pass through the path that includes resistor 1, I've only passed through one resistor. Therefore, if I'm only passing through one resistor, I have 9 volts to spend, and I have to spend all of it before I get back. Hopefully you're seeing that. I must spend all 9 volts in resistor 1. So the voltage across resistor 1 will have to be 9 volts, because if I go across this path, I only pass through that one resistor, and I have to spend all 9 volts. If we take a look at any electrons or any charges, I'm going to start to switch it. Any electrons that go through R2, they're only going to pass through that one resistor. Well, if I have 9 volts to spend, and I'm going through that one resistor, I have to spend all 9 volts. So the voltage across R2 will also be 9 volts. And if I'm an electron leaving this side and I choose to go through the path that includes resistor 3, well, once I return to the other side, as you can hopefully see, I've only passed through this one resistor. If I've only passed through the one resistor, and again, I have 9 volts to spend, and I have to spend all of it, well, if I pass through one resistor, I have to spend all 9 at that resistor. So hopefully you're beginning to see, in parallel, the voltage will be the same. In the previous video, we learned that the current will be the same in series, the voltage may be different. In a parallel circuit, the voltage will be the same, the current will be different. So if we take a look here now that we've filled out our voltage and our resistance values, you can hopefully see again, we can solve for our current using Ohm's law. So in this case, we will take 9 divided by 3, which hopefully you can all see at this point will give me 3 amps of current through resistor 1. 9 volts divided by 2 will give me 4.5 amps in resistor 2. 9 divided by 4 is going to be 2.25, I believe. 2.25. Here's where we find out how intelligent Mr. Walkowicz is or how embarrassed he is. I take 9 and I divide it by 4. He's amazing. Now we all know it. 2.25. So if we take a look, we said at the very beginning the current in R1, R2, and R3 must equal 9.78. If we add these up, you can see it actually is a little bit over. It comes out to about, well, actually, I'm sorry, a little under, 9.75. That has to do with our rounding. But you can see we're fairly close. If we didn't round, we get a much more accurate number. The voltage through any one path, you must spend all of it. Well, if I go through resistor 1, I had 9 volts to spend. I spent all 9. We're good there. Resistor 2, if I pass through resistor 2, well, I spent 9 volts. That's the only resistor I went through. I had to spend it all. We're good. If I went through my third path, through resistor 3, I had 9 volts to spend, went through one resistor, cost me 9, I'm good. Any path that I leave, I pass through, I leave with 9 volts, and I get to the end with 0. So now we know that this is 100% correct. And very quickly, if we take a look, the current is the highest in the second path, through resistor 2. Well, it has the least amount of resistance, so that makes sense. You'll have more current through less resistance. Flip that around. Resistor 3 has the most resistance, so it therefore should have the least amount of current. So if your currents in a parallel circuit add up to your total, your voltage is constant, and you want to triple check your current. Okay, current should be greatest through lower resistances and lower through greater resistances.